So this integral is very similar to the integral of e to the x times cosine x. So we will need two integrations by parts, but we have these extra constants, and we would like to show how to play with these extra constants. So let's start with e to the 2x. So we need to acknowledge a derivative in order to get started with an integration by parts. Let's recall the formula after all. So it's the integral of f prime of x g of x dx is simply f of x times g of x minus the integral of f of x g prime of x dx. Okay, so here we start with the realization that what we're looking at, e to the 2x, is simply the derivative of e to the 2x over 2, right? In fact, if you take the derivative of e to the 2x over 2, the chain rule implies that you will have e to the 2x times 2. That cancels with the 2 on the denominator, giving you simply e to the 2x. So in other words, e to the 2x is absolutely the same as e to the 2x over 2 derivative. So this will be e to the 2x over 2 times cosine of 3x, so we skip the prime. And we subtract the integral where we pass the prime on to cosine of 3x. And actually, let's do this right away. What is the derivative of cosine of 3x? The chain rule again implies that this is negative sine of 3x times 3, right? We think of the quantity 3x as y. The derivative of cosine y is negative sine y, meaning negative sine of 3x, and we need to multiply by an extra 3. So that's going to be e to the 2x over 2 times cosine of 3x. And let's do our usual cleanup. We have two negative signs here, so that will give us a plus. We also have a 3 and a 2 on the denominator that we can extract. And now we can actually assess the situation. Our integral is similar in complexity to the original one, but what we're going to do is perform one more integration by parts. And the little trick that, or the little thing that one needs to know here is that now that you have a choice of what to set as a derivative, you still need to go with e to the 2x. If you go with sine of 3x, you will pretty much go back, cancel what you did before and go back to what you started with. So we insist on writing e to the 2x as e to the 2x over 2 derivative times sine of 3x. And now we're going to perform our integration by parts. And since this is done with this factor 3/2, we're going to write it in front, open a big parenthesis, and perform the integration by parts in there. That's what we should do every time we perform integration by parts and there is a factor in front of our integral. That could simply be a negative sign. So here we will have e to the 2x over 2. And now what is the derivative of sine of 3x? That's, again, by the chain rule, cosine of 3x times 3. So we write that directly. And now we're ready for doing our cleanup. Let's do it. So let's see what we're going to have here. E to the 2x over 2 times cosine of 3x plus 3 over 4 times e to the 2x sine of 3x. And now here we have a minus sign, so minus. And what do we have? Do you see we have this 3/2 in front, and then we have another 3 and another 2. So that will give us minus 9 over 4 times e to the 2x cosine of 3x. We're not going to perform any more integration by parts here. We just note that that's why we put the implication sign, that the original integral that we wanted to compute, which is e to the 2x cosine of 3x dx, is equal to e to the 2x. Let's actually clear denominators here. It will be quite pleasant. Plus 3, oops, I forgot the cosine of 3x here, plus 3 times e to the 2x sine of 3x divided by 4 minus 9 over 4 of the original integral. So the idea now is to bring this integral over to the right-hand side. So again, I'm using the implication sign. And you need to add the 9/4 times this integral. So this will give us 1 plus 9 over 4 here of the original integral. I'm taking the original integral as a common factor. So I have 1 that I had here plus 9/4 that I added. That's why I get 1 plus 9/4 is equal to 2e to the 2x cosine of 3x plus 3 times e to the 2x sine of 3x over 4 plus c. And finally, we can write this as 13 over 4 integral of e to the 2x cosine of 3x dx is equal to 2 times e to the 2x cosine of 3x plus 3 e to the 2x sine of 3x over 4 plus c. Now we multiply both sides by the reciprocal of 13 over 4, meaning 4 over 13. We have a nice cancellation with the fraction on the right? So 4 over 13 gives us a cancellation of the 4. So we really get 2e to the 2x cosine of 3x plus 3 to the 2x sine of 3x over 9. I'm sorry, over 13. And here you would have got 13 over 4 or 4 over 13c. That's the same thing as generic as c. It just represents a general constant that we add. I think we explained that in a previous video. In fact, this computation is so generic that you can even guess what would be the integral of e to the ax cosine of bx dx. So, this is going to be a e to the ax cosine of bx plus b e to the ax sine of bx. And on the denominator, if you notice what we did, 13 is really the square of the two numbers. So it's a squared plus b squared plus c. I mean, we don't need to know the general formula, but it's kind of simple to extrapolate from the computation that we did that this is indeed what is going to come out at the very end. However, we might as well forget about all this, and for the sake of this exercise, it is this formula, which is what we wanted to obtain. And that's all. Thanks for watching.